Welcome. My name is Will McInnes, and this is Taylor Denowden. We're at the Hackeye Institute. We're here in Victoria. And today we're going to be talking about mussel mapping. So using AI to segment drone imagery. And this is interesting for us because we are not experts in marine biology or ecology or intertidal ecology, but we are experts in geospatial and in computer science. So please forgive us if we make any mistakes about the science part of it, but hopefully we can help to understand how the drone mapping and how the segmentation works. So Taylor's going to be leading us today and is a computer science expert in AI and has a master's degree from Waterloo and has been with Hackeye off and on for nearly a decade and has been leading our work in image segmentation and as well as sort of computer science tools for geospatial and for science.
Yeah.
And I'm a GIS person. I do a lot of remote sensing and drone work. I don't know a lot about AI. I'm still learning, so you'll hear a little bit from me today. And I've got a lot of the same questions, so feel free to drop any questions in the chat. And if we find a lot of questions about a certain thing, we'll stop. And the first half is going to be a presentation. The second half, for those that are interested, we're going to dive into the data. So I'm going to be the guinea pig who's going to share my screen and go through the instructions of how to use the tool. I've only done it once before, so it'll be a good way for us all to learn together. And then Taylor's going to be taking on sort of helping to troubleshoot. We've also got some data. I'll share that in the chat. So if anyone wants to download, if they don't have their own imagery data and they want to try and see how it works, they can do that. So I'm going to pass it over to Taylor.
Yeah, so welcome everybody. Okay, so just to go over a little bit of what we're going to talk about in the presentation, we're just going to kind of introduce the problem and sort of the different methods for mapping mussels in imagery. And then I'm going to talk a little bit more about, go into more detail about deep learning. So talk about the different kinds of image classification that we can do, the different kinds of methods that are available to us, deep learning being one of them, but also talking about sort of classic approaches. And then I'm going to talk a little bit more about implementing deep learning and what that sort of looks like, how to prepare your data, and sort of the tricks you can use to kind of make it perform better. And then finally, we're going to talk about some work that's kind of in progress and how you might be able to sort of adapt these models or these techniques to your own data sets or other kinds of data. So to get started, many of you are probably nearshore ecologists or scientists who are maybe more familiar with this than I am. But mussels are kind of interesting because they're keystone species and an important source of like habitat and food for a bunch of other animals. And so monitoring how much they're growing or present in an ecosystem is kind of an interesting thing to look at in terms of monitoring overall ecosystem. There are kind of a couple techniques to map mussels, one of which is to do these kind of in situ transect surveys. And so this is a nice method because you get a lot of detail, but the downside is that it's pretty time consuming. You can't cover a lot of area, and it can also be like pretty dangerous if you're on rocks kind of in exposed intertidal environments. And so the alternative is to do drone surveys where you maybe don't get as much detail about what you're looking at just due to restrictions with resolution. But you can cover massive areas and maybe get an idea of the total area coverage of mussels. And so we're going to kind of focus more on the drone side today. But that's not to say that there is not value in still doing in situ surveys. It's just kind of a different goal of each of these methods.
Just go back for a second. I'll just point out Alyssa there, who's on the call as well today, who's our scientific leader. So thanks, Alyssa, for spurring this on and for helping us learn about mussels.
Okay, so right now with drone surveys, sort of the most basic way to, track mussels between imagery is to manually go in and trace the mussel beds in GIS software. It's usually a pretty accurate way to do this, although it's extremely time consuming and also pretty boring work. So our goal with this deep learning tool was to try to automate this as much as possible, both to relieve people of kind of doing this sort of like uninteresting work so they could do more interesting research, spend their time doing more interesting research, but also it allows us to kind of scale up and cover a lot more area and map drone beds a lot more efficiently. So we can cover more area in a year and maybe kind of answer more interesting questions as a result. Okay, so when we talk about image classification, we often kind of use the term quite loosely, but as it pertains to like deep learning, there's kind of a few main, more specific terms that correspond to what people usually use casually for classification. So the first is what is just called image classification. It's putting a label on an entire image. So if we see this image of a pelican, the classification problem is like seeing this image, what is in the image? And so the answer would just be pelican. It doesn't tell us necessarily how many pelicans there are in the image or where they are. And for images that are a lot more complicated than this one, it's kind of hard to put a label on a complex intertidal scene to say like this is mussels or anything like that. So to get kind of more specific, you can do what is called object detection. So what object detection does is it tries to label a set of known objects in an image and also mark where they are. This is really useful for if you're counting things. So if you wanted to count the number of birds in a scene or the number of boats in a satellite image or something, this is kind of the technique you would use. But today we're going to talk more about semantic segmentation. And so what semantic segmentation is classifying individual pixels. And so it doesn't necessarily tell us how many individual species there are, but it does give us a good sense of area and lets us kind of track, questions pertaining to area and what composes, what are the different like sort of compositional elements of an image overall. So when we talk about these labels, what we mean is that what it looks like is we have a paired image along with our input image, which is the mussel image that you're seeing. But we also have this label image that is identical dimensions, and all the pixel values are just an integer. And so in this case, we're using an integer value of 0 to mark class other or not mussels, and pixel 1 to say mussels. And so if you wanted to map multiple species, you would just add another pixel value. That would be 2, and maybe you would call it, gooseneck barnacles or water or rocks or whatever else you were interested in. And then you would just have a model that predicts all those classes. So it doesn't necessarily need to be a binary classification problem like this. Okay, and then when we talk about modeling, this is kind of the setup that we're imagining. So we have some input data, which in this case is an image, and then we have some sort of model or method for transforming that input image into what we want as our output. And so in this segmentation problem, the output is that mask image that marks where the different things are. And so we want to produce some model, and there are multiple options for this that we'll talk about, that is able to kind of map that input to this mask as the output. And then from that mask, we can do further analysis, looking at things like area over time. Okay, so traditionally, this model is often kind of these simple statistical functions that say, if the input image has red pixels, blue pixels, and green pixels that are all below some level of brightness, maybe we'd call that a mussel. Otherwise, we'd say it's something else. There's kind of more complicated versions of this where you also look at things like texture or shape of objects. And they can work really well, but the downside of these things is that they all rely on these handcrafted features, things that we have to come up with as descriptors to help differentiate between what is a mussel and not a mussel. And so often we call these things features, which are just attributes of the data. that help to make these decisions. So that might be, the brightness of the red color channel in the image. Sorry. It could be rugosity of the image. So something that's like derived from that input imagery. Another classic one, if you're familiar with sort of remote sensing, would be like NDVI, where you're looking at the proportional values of different bands in the case of NDVI, usually pick up vegetation. Yeah, so these features, these models can work great, but they don't necessarily work across scenes that well. And that's because typically you have imagery with different lighting conditions, different weather. And so those models kind of can quickly fail to perform once you start putting different data into those models. And so I think Will's gonna talk.
Sure, yeah. So I wanted to share a little bit here and talk, I'm gonna talk a little bit about remote sensing. And remote sensing means, when we're looking at this picture, or any picture, we're not looking at objects, we're looking at reflected light. And so we need to think about how we're going to get the computer to convert what we see light reflected into sort of objects like a map of mussels, for example. So here I wanted to show on the left, we've got images flipping through. This is our North Beach survey site, and those of you with a keen eye on the intertidal are going to see a lot of change in seaweeds and mussels and other cover. What I see is a large variation of color. So it's darker, it's brighter, some of them have more or less contrast. And what Taylor was talking about, classification, a lot of traditional remote sensing designed for satellites, we might say, well, we expect water to be blue and rocks to be gray and mussels to be black. But because of the variation of color, we can't just take those values in drone imagery and compare them. And in fact, and even within one scene. So the graphs I've created on the right here, each row is an individual scene from 1 year, so 2022, 23, 24. The colors are different bands. So our cameras, just like our eyes, we see red, green, and blue. And the computer, those get split into 3 different bands. Your camera sensor, the values there, you'll see they go up to 255. You might know that's 8-bit. So a typical sort of consumer camera will be 8-bit, and each time it takes a picture, it's just registering values in those bands. So it says, okay, each pixel is blue 100, green 200, and red 0 or something. And so what I did is I took some samples to try and figure out, well, I wonder if we could tell these apart by color. And if you look at the overlap between, for example, background and mussel in each of these, there's a few areas where you might get a decent, for example, 2022 green. There's some chance you'll get an okay classification. But for the rest of them, there's so much overlap and so much range of data that we can't just use these traditional color methods. Because if we said, okay, well, it's sort of black as mussels, well, you look, that's also going to get shadows in some images. It's going to get the ocean in some images. So it just doesn't work, and that's why we need to get more information. These are a couple images I'd like to share because it's good to compare the drone imagery to sort of what we see up close. And just to point out that for remote sensing, it's all about what the sensor can see and not about what's really there. Sometimes we call it surface reflectance. So in the left-hand image, we've got probably what's typical for us, which is a mix of mussels and some fucus and barnacles and all sorts of stuff in there. And you all may be able to immediately intuit that, okay, there's if you're there surveying and with a quadrat, you'd be able to see that there's mussels underneath the fucus, for example, or mussels underneath the barnacles, but all we can see in the remote sensing is what's on top. We also can't tell the depth of any of these things. And on the right hand is an interesting one because we've got a mix here of barnacles. I think some of them are white because they're bleached, and perhaps Alyssa can add something in the chat if I said that wrong. There's also gooseneck barnacles in there, which are also white. And there's also barnacles that are also kind of white. So it's a challenge of trying to tease these apart. And what we're looking at here is not individuals, but sort of beds and what we can see in the images in the plans. In terms of sort of the color and contrast, I like to show this one. This is a great comparison to sort of satellite imagery versus drones. You all may be used to, oh, thank you. Sorry, the mussels were eroded, not bleached in the last image. Thank you, Alyssa. Sorry about that. In satellite imagery, so if you go to Google Maps, for example, everything is sunny. You might see the odd cloud, but whenever you see the ground, it's sunny because if it's not sunny, then you can't see the ground from a satellite. Clouds are in the way or shadows. But the advantage of the drone is we can sort of fly almost anywhere at almost any time. We just need a little break in the rain and not too many clouds. So sometimes, like on the left here, we get a sunny day. This is out on a little rock a few miles off the west coast of Calvert Island. So we're basically at the edge. Behind that rock is sort of with a lot of ocean, and then Japan. And on the right, just a different day, and it's completely overcast. And when we look at the close-up drone imagery on the top there, we see sort of on the left, it's brighter, we get a lot more contrast, but also we have shadows. And on the right, it's much more muted. But we can still identify mussels and gooseneck barnacles with our eyes. So in theory, we can just have to figure out how to teach the computer to do it. But we can't just say some certain level of brightness or something like that, or, you know, an edge or something like that. So we need to use the machine learning tools so that we can use this variety of image. And the magic of the drone is we can collect a lot of data really fast, but it's not necessarily very good data. It's very noisy. The satellite, for example, the bands are all calibrated. It's designed to work in a certain lighting range. The sensors, the camera always takes a picture around noon. The drones, sometimes it's early in the morning to catch a low tide. Sometimes it's evening light. We need to come up with algorithms that can capture the features under all those conditions. I also wanted to talk briefly about near infrared because it's a question that comes up a lot. Something we've explored a little bit. So near infrared is light. It's like red, green, and blue. And if we think about, if you've ever seen the electromagnetic spectrum diagram that goes from, if you can imagine radio waves and microwaves and FM radio and all that stuff, X-ray and gamma rays, near infrared is just next to red. And plants reflect very highly in infrared. So sometimes if you see, here's an image, a near infrared false color, we call it. So the red band here has been swapped out with a near infrared. So the vegetation, so you see the tops of the kelp and some of the algae there is reflecting very highly. It's bright. And you could go to the next one as well. And this is, it looks like sort of a Cold War spy satellite image or something. This is just near infrared band only in grayscale. And you see again, very bright vegetation, and the water is very dark. But the challenge with working in intertidal and anywhere marine and near infrared is that near infrared is absorbed very strongly in water. So if we think about this image for a second and flip back 2 images to the color, suddenly now we can see into the water. And we can see a lot more of the front of the blades of the kelp, for example, that are all underwater. So if we think about the intertidal, near infrared may work, you know, above the water, but the problem we often have is we have waves, we have varying degrees of wetness, often because, you know, we don't want to classify based on how recently the tide had been hitting something. And then if it's stormy or it's been raining, forget about it. It doesn't work. So it is an interesting concept, and there may be some niche where it does work, but generally we work with RGB because we found that the texture and color information is a lot more useful than adding infrared. Thermal is one that may have some more potential, but it's got its own challenges.
So we've already stated this a few times, but yeah, the sort of fundamental limitation of a lot of traditional classifier techniques is the need to have to come up with those features that help you differentiate between mussels and other things, or whatever you're interested in. And so the deep learning approach kind of solves this problem for us by automatically figuring out what features are useful for differentiating between your classes of interest. What it does is you sort of start with your input image values, so your RGB pixels. This is kind of a simplified view of how these models kind of work, but I think it illustrates the point. So you start with your RGB pixel values, and then you do a series of transformations within this model. And so the first transformation is figuring out a bunch of things that are combinations of your input values, RGB pixels in this case. And then you can keep doing that over and over again. And so the next layer will take combinations of those combinations. And you can do this and generate, millions of combinations of features that are eventually used by some final layer to figure out the probability of a mussel. And I'll talk a little bit more about how the model generates these features, but it does it based on how accurate that probability is, and then updates the features so that they're more and more useful. And because we can generate, millions of these things, we start to have redundant representations of what is a mussel and is not a mussel. And as a result, they tend to work pretty well across different scenes. And you can also train them so that they take into account that the lighting conditions might change sometimes, and they'll kind of compensate for that. Yeah, one thing to maybe also point out is that these models are not necessarily silver bullets for all kinds of problems. You still need some sort of input signal. So this image kind of shows a dark area where it's pretty much impossible for a human to tell if those are mussels or just shadowy rocks or seaweed or something else. Deep learning won't necessarily solve that problem for you. There needs to be, some kind of signal from your input that a human could, draw around and figure out what's there. If that's not possible, then the model probably won't be able to either. And then finally, I just wanted to quickly mention a couple downsides of deep learning. So it generates these features for you, but one thing that hasn't progressed very far in sort of deep learning literature is how to have the model describe what those features are in a way that is easily interpreted. So it's really difficult to kind of understand how they make their decisions, even though they often, experimentally will be quite accurate. But this can be a real issue for safety critical applications or present ethical issues. The other thing is that they can be kind of complex to tune. There are a number of tools that kind of let you implement these things in software like ArcGIS semi-automatically, but to really squeeze all the performance out of them and get them working better than a lot of the traditional classifiers usually requires some technical knowledge to make tweaks and get it performing to the maximum ability that it can. And then finally, these methods are super data hungry. And so what I mean by that is that the models kind of learn by example. And so the problems that are best for these kind of training pipelines are problems where you already have a lot of data that maybe have been generated via much slower methods. This mussel problem for us was suitable because we already had a lot of data that was painstakingly hand labeled, and we could kind of use that to train a model so that we didn't have to do that anymore. But yeah, we often hear a lot of questions about, can we implement a model to make this task a lot easier? And people sometimes are disappointed to hear that we can't do it without them doing it the slow way first. Okay. And so I'm going to talk, or I guess Will's going to talk a little bit about data collection, and then I'll go into some detail about how that model training sort of works at a high level.
Thanks, Taylor. So I think a lot of you have been involved with some of this drone mapping, and I've seen, in fact, some of the folks on the call, thanks, because they provided data that's helped us train our model, because we work in British Columbia on the northwest coast and the Pacific coast here, and so we only see certain scenes. But but we're out with our drones. We use a few different drones. The Phantom here has kind of been our workhorse for a long time. We're using a Mavic now, a smaller one. We've also looked into, there's a lot of sort of, I guess you would say scientific grade drones, larger, more complicated, different sensors. We've tried a lot of different things, and we've landed on this platform because, we're working from boats. We're in production mode. We do probably, we average over 100 different missions every year. So we collect a lot of data. We need to be able to be sort of agile, fly from a boat, hike to a location. In fact, we work in the snow, and so this has been great for us. And the imagery lends itself well to the machine learning approaches because it's sort of standardized in a way that the consumer style camera, it's normalizing each image, so it works well. So we hike or boat to a location, and we set the drone out on an automated path. So in the bottom right here, that's an autopilot mission and we set out an area of interest, and the software draws flight lines based on our parameters. So we set how high we want to fly, how fast, how much overlap. And generally for the Mussel mapping, we're looking for like 0.5 to 1 centimeter pixel resolution. So that's the smallest thing we can see is about 1 centimeter. And that translates to 15 to 40 meters high, roughly. It depends on where we are, what sort of hazards there are, how long we need to fly, those sorts of things. And then we set the drone off, it goes and takes pictures. And we use structure from motion software. So we use either Edgesoft Metashape or Pix4D mapper, and it takes the imagery, looks for tie points, so matching points between images, and turns the individual photos into 3D point cloud, and then a orthomosaic elevation model. We'll use ground surveys where we can. So this example is part of a marine multi-agency Rocky Intertidal Network site that we set up last year in West Vancouver. And so we were out with RTK GPS and ground control points. So we have really accurate heights, and we convert that to chart data. In areas that we can't get to, some of our more remote rocks, we use the tidal height and adjust based on that. And then we can take measurements in the data. We can calculate area in 3D, which is important, and sort of look at things like what are the high and low lines of mussels, things like that. And then the next part is the data labeling. So we talk about the input data to the model. And what is that? But it's a lot of labels, which sort of means somewhere that says these pixels are mussels, these are not mussels. And a lot of it is what our colleague Alex was doing here, looking at imagery, drawing mussels in manually in our GIS, can be done in QGIS. We also have worked a little bit with object-based segmentation. The middle tile here is from something called ecognition, thank you, where it's a sort of semi-supervised method of segmenting an image into pieces and then trying to come up with rules that say, whether something is a mussel or not. But we have to do that scene by scene because the problem I was describing before with color. We've also tried a little bit elastic, which is the one on the right, which is again, a semi-supervised machine learning method where you're sort of drawing like in paint, you're labeling things, and on the fly it's trying to calculate based on a bunch of different features. So abstractions of images. So for example, the image would be blurred or edges, and it's trying to come up with rules for how to classify. But again, it doesn't work that well because the scenes are so varied in terms of color. Designed for medical imagery, where you're looking under a microscope and the light is like fairly consistent. So that we end up just going back to the manual labeling a lot. And I think of this also in terms of like, you've heard a lot about some big machine learning models, so like language models like ChatGPT, and they're loading in, this is where it gets a little bit questionable of the ethics, and they're loading in millions of pages of text, of books, of the internet, all sorts of stuff. And for self-driving cars and imagery, if you've ever been on Google's reCAPTCHA and it says, which of these have a motorcycle? Well, it's testing you to see if you're human, but you're also helping them to build their machine learning database. And so all just to say that these models require a lot of these inputs. Is that right?
Yeah, that's fair.
Yeah.
So after we kind of label these giant mosaics, we maybe counterintuitively go back to splitting them up. We split them into these chips basically for computational efficiency reasons. We need to be able to load a bunch of these chips into our neural network training pipeline at one time. And it helps if they're all standardized. And so for this Mussel model, we had 39 labeled mosaics, and we split those into chips of square chips that were 512 pixels square. And so this resulted in about 4,800 image tiles. I think we used about 80% of them for training our model, and then we left the other 20% for validating our results to make sure that we didn't kind of make a model that only works for those training chips and would work for new images as well. So to effectively create a data set for training, it needs kind of a few things. The first one is standardization, which we've talked about quite a bit, but making sure that all those label images are consistent. There's no like weird extra values. Making sure that your images are similar. They all have the same range of pixel values. So often this means standardizing your bit depth to byte type or unsigned integer, which all this is just kind of technical ways of saying that the pixels have a range of 0 to 255, and that you don't have any pixels that are -1 or 256 or something to mark where there isn't data. Instead, what you should be doing is using no data metadata values in the image so that your model can use those to figure out what areas are blank imagery. The second thing is that these models, because they are learning by example, which I'm about to talk about a bit more, you need to give it good examples to learn from. So a common phrase is that if you put garbage in, you'll get garbage out. The model can only really replicate the human labeling process to the accuracy that the humans have labeled it. And so if you miss big beds of mussels or you label things that aren't mussels as mussels, your model will probably suffer in performance as a result of that. And then finally, you should have some realistic variation in your data set. So if ultimately you want to create a model to label imagery in all kinds of weather conditions and different lighting, it's ideal to have a training data set that is sort of representative of those conditions, which might mean you have to go and fly in the rain and then label those images. And they might be harder to label than the sunny images. Okay, so I've kind of alluded to this learning by example process a little bit. So I'm going to talk a bit more about that. The model training workflow is kind of this. So you have your input image, and then you have your known labels that have been handmade or hand labeled, and you have your neural network model, which is similar to that chart that I showed with all the nodes and lines. That neural network model is initialized just randomly. So you put your image in and it spits out something that looks pretty bad initially. But then you compare those, inaccurate labels with the ones that you are assuming to be totally accurate, and you calculate some amount of error on those. And the reason that we do this is that we can then use that error to update our model. The way that this works is via calculus, and I'm not going to go into too much detail about it, but we can take that error, which is often called loss in this context, and use it to bump the parameters of our model so that we expect the loss to decrease, and we do that with calculus and derivatives. We do this process over and over again. So we go around that loop from input image through, calculate error, update parameters, thousands and thousands of times until the loss is kind of hits some sort of minimum plateau. at which point we say our model is trained, and then we can reuse it to classify new images. And so when we're ready to use it, we just keep the neural network part and we can feed in any image without necessarily having known labels, and it'll spit out predicted labels that we expect to be reasonably good. So before I kind of talked about how it's nice to have realistic variation, but one way that we can kind of artificially introduce this is through this process called data augmentation. And so we did that a lot with this model. What data augmentation does is it randomly sort of transforms that input image so that it replicates, conditions that you might see in the real world, but without you needing to go and collect all of them. And so here's some examples of that that we do. We'll flip and rotate the image randomly and blur it, add noise, change the color. And all these things are kind of meant to imitate, the kinds of non-ideal data that we might be collecting and have the model learn to kind of ignore these confounding factors. In the case of mussels, the orientation of the image shouldn't matter. So flipping and rotating the image helps the model to learn that, it's a mussel bed no matter which direction it's facing. And same with motion blur, like we might have drone imagery that is kind of not ideal because of maybe low light conditions, and as a result, it ends up being slightly blurry. We try to kind of get our model to compensate and allow for that sort of non-ideal imagery and still perform well. And so this can, really help us by sort of artificially inflating the size of our data set to represent more conditions. Okay, so after we've kind of trained our model, in the case of mussels, it works pretty well. This is kind of an image that is new and wasn't used in the training pipeline, and we found, by looking at that held out set of chips that we created, that our model was able to recall about 92% of the pixels that a human called mussels. And of those that it labels as mussels, it's right about 96% of the time. And then finally, we calculate a metric called Jacquard similarity, which is often called IOU as well. And what this is a measure of the agreement of the predicted model labels with the human labeled ones. So the name IOU stands for intersection over union. So what we do is we kind of treat our labels as two different shapes. We take the count of pixels that intersect between the predicted and the known ones, and we divide it by the total area that both of them cover, the union of those two shapes. Qualitatively, we can see that it works pretty well. The green here is showing the labels that are in agreement between the humans and the machine. We see some errors kind of on the fringes of this in these sort of transition zones. That's not terribly concerning. There's a couple areas where it's detected mussels in dark zones, places that probably humans have a hard time detecting mussels as well, or differentiating between shadow and mussel. And then we also see some areas where the model is able to pick up mussels that the human labeler had missed. So there's that purple splotch kind of at the top. That was something that would have been missed by somebody labeling by hand. But by doing things like data augmentation, we kind of encourage our model to learn a fairly general model where it might be able to compensate for some labeling inaccuracy, and in this case it did. Do you want to talk about this?
Sure, yeah. So one challenge we're having is that our mussel model is not tuned well to deal with gooseneck barnacles. And it's something we didn't think about a lot initially because the sites that our field teams visit don't have a lot of gooseneck barnacles. And that's because it's, a lot of these outer exposed rocks where they live are just too dangerous to survey in or hard to get to. So we're now working on improving the model and adding gooseneck barnacles explicitly as a class. And so that means we need to do a lot of labeling, and it's led to some challenges and questions for us because, in some cases, as I showed before, the goosenecks are mixed in, but Yeah, so we're working now on adding that, and then also other species, because we get questions about, algae and other things. So trying to figure out how we're gonna do that. Our goal would be a general model one day that we just sort of put in an image and it pulls out, any of the land covers we're interested in, mussels, goosenecks, fucus, kelp. But we're trying to do it one piece at a time because it is quite intensive to get the training data. And that's where we're excited to share some of this work and find collaborators so we can expand our sort of training sets, and validation sets. So it's been great to have some data from California and Oregon so we can test, because it all looks a little bit different. In fact, we were surprised to find out we'd never put an oblique image like this in, and we just threw sort of a bunch of random images in, and it actually was able to even detect mussels fairly well on an image like this.
Okay, so the next part of this workshop is this tutorial on how to install and use our Mussel model. So if that interests you, you can stick around. But maybe before we do that, we can open up for questions.
Yeah, absolutely. Yeah, if anyone wants to either type in the chat or raise your hand if you have questions, and then we can answer those now. And if not, we can look at some computer stuff. So I'm just going to share a couple resources here. So put it in the chat.
So Alex is asking what kind of model did we use for the classification? So we tried a lot of models. The one that we settled on was called UNIT++. And so it's a convolutional neural network, which means that I showed sort of a simplified picture of the deep learning model, but the convolutional model, the way that it differs is that it actually processes patches of 3 by 3 pixels at a time, for example, and then it builds those up in kind of a pyramid. So it does these kind of iterative transformations of patches of the image, and it learns to detect things like texture as well as just combinations of the pixel bands. This is kind of one of the current sort of state-of-the-art methods for image segmentation. Other models we tried were DeepLab, and a couple of vision transformer models as well.
So Emily's asking, were you able to gain insight into what predictors were most important for distinguishing mussels? You mentioned it was able to distinguish shadows and dark rocks from mussels. What do you think it was picking up on there?
So no, we weren't really able to tell, and that's because of sort of the black box nature of these neural networks. Yeah, I think that probably texture is quite important just because mussels look pretty different in imagery, but it's purely based on speculation. Yeah, there's some work in the machine learning literature that towards like model explainability, but they're still pretty in their infancy, so they don't really give us very interpretable descriptions of like what is actually being used.
Yeah, it's an interesting question because prior to these machine learning methods, we did a lot of work to try and build classifiers. So using sort of traditional pixel-based techniques like supervised and unsupervised, and also a lot of time in the ecognition. So what you're doing there is you've got one layer where you're trying to segment, so you're trying to draw boundaries around things, and another where you're trying to figure out what it is you've drawn a boundary around. And there you're creating these features, some of the ones that Taylor was talking about that look at color and texture. And it was quite challenging to come up with anything universal because you're also looking at different scales. So you're resampling the image, sort of blurring it. And the imagery also is quite variable. So we found that, if you get imagery that's too high resolution, then suddenly you're looking at individual mussels, you're looking at barnacles and seaweeds. And if you go too far away, then, you're just looking at blobs. So trying to come up with the exact, well, the shadows or the muscles, we need to use an edge detection algorithm at 9x9 or something. It doesn't really work. So that's why we didn't have a good answer there.
So Alex is asking how much the work we've done can be transferred to other kinds of imagery and data. I kind of have two parts to this answer. We've tried to set up our model so that it will work quite well on mussels in different areas. And so one of the data augmentation steps we've done is play with the amount of image resolution. So we kind of dynamically lower the image resolution to try to make it work for drone imagery that has maybe been flown at a higher height and lower resolution. But as far as transferring it to other species, it's been trained very specifically for mussels in this case. So it won't work off the bat for those mussels. However, if you had a different data set, you could reuse the kind of architecture of our model and rerun that training pipeline on a different data set and get decent results as well. There's no guarantees that sort of the model we've chosen is going to be the best model for every kind of species. And you might need to kind of play with that architecture a bit, but it tends to work pretty well for segmentation overall. We use a model that is known to perform pretty well for these kinds of tasks. So it should work pretty well for other kinds of tasks too. But the best way to kind of tell which one is the best is just by trying a bunch of them.
Do you want to talk, Taylor, about, so you'll see, I dropped it. Did I drop it in the chat yet? No, I will. There's a link there called Kelpomatic.readthedocs, which is what we're going to use in our tutorial here in a moment. And so this model that we're using, initially we created one for mapping kelp. So you'll see it's weird, why are we using this Kelpomatic thing? Taylor, do you want to talk about maybe the difference between, in this vein, like how those models are related, if at all?
Sure, yeah. So this is called Kelpomatic because a lot of this work was actually originally done for kelp detection, which looks like this. We were able to kind of reuse our models for kelp detection, or a lot of the same sort of setup for loading our data and running that training loop, but just kind of load in different images and different labels that correspond to mussel habitat. And as a result, it was easier to distribute this using the same kind of package that we distributed our kelp models in. So that's why it's called Kelpomatic, but it does work for mussels as well. What was the second part of your?
Yeah, just whether how they were related, and I guess just in the vein of the question there.
Yeah, so I mean, to extend on it further, yeah, you could definitely copy the code we have, which is online and available. But you'd have to prepare your data set for whatever species that you were hoping to look at, and then rerun that code to train the model. Questions, or should we move on?
For the gooseneck barnacles challenge, have you tried a distinct mixed class for area with mixed barnacles and mussels? I found discrete mixed or unknown classes to be very helpful in semantic segmentation.
We haven't tried that. No, most of the issue we've run into so far is just lack of data availability. So we don't really have a big data set that has labels for mussels and goosenecks. We could introduce a mixed class, but then it becomes hard to measure accuracy because if there's a small patch of goosenecks in a big bed of mussels and it says it's mixed or it says it's goosenecks, both are somewhat right. So it becomes kind of hard to measure performance and determine when your model is working well. So I tend to prefer discrete classes that don't have any overlap, but it might be something, I'll think about some more.
Yeah, it's interesting. It's something we've been going back and forth on a lot, because if we think back to an image, sort of there was mussels and barnacles and eroded mussels and gooseneck barnacles, we have a hard time at the scale that we map at telling the difference between individual mussels, individual gooseneck barnacles and mussels with barnacles on them or eroded mussels, for example. So we don't want to start sort of diminishing our mussel data by suddenly saying, well, this is mixed, when it may or may not be.
One thing that we've done in our kelp model, we have a kelp model that detects two kinds of kelp, macrocystis and nereocystis. Is in our hand labeled data set, we introduce a sort of a mixed class that we actually call an ignore class. And so what happens with that is in our training loop, any sort of update signal to our model parameters that come from that ignore class area are discarded. And so instead of our model trying to learn from complicated data, which may have not been labeled very accurately, we try to just label from the things that we feel confident that we got labeled accurately. And that's helped us a little bit to come up with models that work okay in those mixed areas that are hard to label.
Perfect. I'm just trying to create a poll here. I don't know if this is going to work, but yeah, let's move on. And what I'm going to do, let's see if this. I'm going to start off with a little bit of a tutorial on command prompt, or I should say terminal. Okay, you stop sharing and I'll share mine. Okay, yeah. Okay, we're good now. And so if
Yeah, I'll field the chat. So if anybody runs into any problems, I'll try to resolve them in real time and we'll do our best. This is the first time we've tried to do a live tutorial online like this. So be patient with us, but we'll try to make sure everybody can get up and running and try this out.
do you want to put my screen up there, Taylor, so you can maybe just put it as a tab? And then Taylor can help me and critique me here while we're going. And yeah, if anyone wants to drop off now that isn't interested in this part, feel free. I thought because people are always asking, okay, what is the model? How does it work? And it runs in command line, so the actual running of it is not very exciting. But I thought it would be useful here to show a little bit of terminal, just because often I find when I'm working with computer science folks, they jump straight in and they're like, oh, just do this, go ahead. And it's a little bit scary. So that's why I'm running things. I'm on Windows here. So if you have Mac specific questions and you're confused, please drop that in the chat. Taylor's got Mac. And I'm going to use PowerShell, which the commands are very similar to what would be called terminal on a Mac. I'm starting here in a folder. This is a little trick that I learned that's super handy because now I'm not very good at navigating in terminal. And so if you right click in a folder in Windows, you can go open in terminal and it will open a PowerShell window at that location. So here we are, we're showing in the little bar here, we're in a folder in my documents that I created called Mussel Seg tutorial. If we want to see what's in there, we can type, maybe I should do it in Windows, in Mac commands, ls.
Sure.
And then it'll show you the name of all the folders. So I've got 2 folders, inputs, outputs, and a little text document that I've actually got open here on the side. Those of you who are power users can edit text in PowerShell, but that's too scary for me, so I'm not going to do that. But I find for working with terminal, it's handy to have a notepad open so that I can save commands and edit things that I'm going to reuse. I'll often, like if I have a workflow for something that I do often, I'll just save it in a text file so I can copy paste.
Maybe just quickly, so the output from that ls command is showing what's in that folder where we'll started this from. So if you move the shell over,
Yeah,
yeah, the shell, the PowerShell or terminal is just a different way to kind of navigate the file system and run commands on your computer. So those two things are the same. There's a little path at the beginning of the terminal that says users will documents. That corresponds to the same location in the file system.
yeah, exactly. Yeah, and I'll just type, so if you've ever seen in Windows, I used ls because PowerShell allows both Windows and what would we call Linux? Unix commands. For Windows, it's called dir, which is the same thing. So that's listing the files you have. If you want to move around, use a thing called CD, and you can either type the name of a folder that's in there, you can type a full path. If you type CD and 2 dots, it'll go up a level. So you see now I'm in my documents. I can type in, oh, I'm scared for everyone to see what's in there, but we'll find out. This is all my garbage that I have on my computer. And then if I want to go back down, this is where we learn tab is super handy. So we can start typing. I'm going to just type an M because I'm going to go to this Mussel site. Oh, I should type MU. And if I hit tab, it'll start showing me different options below there. And then if I just enter, I'll go back to where I was. And now I can see that way, see what's in there. And so that's sort of the start of it. In Windows, you can paste stuff by just right clicking. So if we have an example, this should just be example command test. And I control C to copy that. I go back to my terminal and right click, it'll paste it in there. Another handy thing is if you go, I'm using the up arrow here, it'll go back through all the different recent commands you've done. And that in PowerShell, probably in terminal too, it'll save them from different sessions. So it's handy. Some of these commands you'll find are a little bit long if you're writing paths. So it's handy to go back and retry things. And you can go back, you can change it to something else if you want. And if you make a mistake, it'll tell you. What else did I want to talk about for?
Maybe you can navigate multiple paths at the same time too. You just separate them with slashes. The difference between Windows and Mac or Linux is just the direction of that slash. So Windows uses backslashes, I think they're called.
Yeah.
Those ones. And then if you're on Mac, it's just the other
right.
slash.
Yeah, this way. That we're saying. Yeah.
Yeah, and that's like one of the main differences, really.
Perfect. Yeah. Okay, so that's sort of the start of PowerShell there. If you look up, you can look up cheat sheets for these things, which are super handy. I have them printed off on the wall for various different commands, things that you could do like, you know, saving to a text file or writing a tree. You can, you know, have it tell you all about your network, what your connection is. There's all sorts of fun little things you can do in there. But this is where we're going to install Helpmatic. So I'm going to go back to, and please, yeah, if you have any questions or you're lost, let me know and Taylor can help out. I'm going to open this up here, which is the instructions. And I'm going to go over to the beginner guide. There's also a terminal crash course in here. So thank you, Taylor, for that. Yeah, so just the same thing, CD, slashes, how to use, how to change directions, what to do about spaces. And what Taylor set up here, which is great, is creating what's called a virtual environment, which she can correct me here, but it's sort of a little box where all the installation is going to live in that's separate from your computer so that you can work in that area installing Python and packages, and it's not going to interact positively or negatively with anything else you've previously installed. So we've had a lot of challenges trying to get this into a format that works for everyone. And like some folks, for example, if you have GIS, ArcGIS or QGIS already installed, it's got its own Python. There's all sorts of problems there. So creating this virtual environment.
Sandbox, yeah.
Yeah, the sandbox, exactly. Did you want to add to that?
No, that's kind of the main thing. Yeah, your computer probably likely has Python installed already with its own packages that it uses. And so This is just a way to kind of keep things separate and making sure they don't interfere with each other. There's a bunch of different ways to install these kind of like, sandboxes or more technically called virtual environments. One is called UV, which is what we're going to go over here. But if people have used Conda or other kinds, those also work. But UV is kind of new and it's pretty slick. So that's what we're going to use today.
So yeah, this reminds me of a couple of things related to that. One is the path, all caps path, if you've ever seen that. And environment variables, which is that the same terminology for Mac and Windows?
Yeah.
So these are sort of preset paths that your computer knows in terminal where to find things. So for example, when I typed in ipconfig there, that's a little executable that's stored somewhere. The computer knows where to look. When we install Python and someone says, oh, just type in Python, your computer has folders that it's looking for. So if there's ever issues where it says, I can't find whatever program you're typing in, that's what the path is about. So you can look into that a little bit later, but do I want to say anything? No.
Yeah, so we're going to go over how to install this virtual environment manager called UV. The best way to do this is really to just copy and paste these commands, because typing things in manually is kind of error prone. There's documentation on the UV website about how to do this, but we kind of repeat it here. So if you're on Windows, you're going to copy this command. If you're on Mac OS or Linux, you can go to that tab and copy that command and press install. And it's going to download for a little while. It might ask you questions about if you want to proceed, and you type in yes or no, press enter.
So yeah, so I've just done the first one here. I've just copied this. Yeah, as Taylor said, you can click on this Mac thing if you're going to do it in Mac. And this first one is just this is installing the UV program. And the execution policy. Sometimes in Windows, you may end up with warnings about permissions and things. So it's especially, trying to protect you from installing random software that people have developed like this that may harm your computer. And so we're just trying to get past that. So this is where next thing we need to do is go to where we want to create our virtual environment. We've got CD here, which is change directory to where we want to do it. Can I just install it right here if I'm letting it happen? Yeah. Okay. And so this is where here you need to do some typing. So UVVN is the command, just UV create a virtual environment, and then you'll make a name for it. And I'm just going to call it Mussel Seg. That should work. And we'll see if anything happens here. And so there we go. So it's now created the virtual environment. And if anyone is following along and trying this, let us know if you are able to do it or if you're having some errors or trouble.
This is kind of the most complicated part of this, and often where we run into Windows permission errors. And there's that little orange box on the documentation here, which allows you to resolve issues about permissions to create a new virtual environment or install UV. And so it's just another command you have to copy in to that set execution policy sign down there.
Perfect.
And that should resolve those
Should I run
errors.
that one just?
Sure. I mean, you probably already ran it.
I've already do, but I'll just run. And thanks for that feedback, Ray. That's great to hear. Because we're always trying to test these instructions on different folks, and sometimes it's hard to find people that haven't that are sort of fresh, that haven't seen it already. So it's great. Okay, and so now here's where I can activate it. So I do this / and I call my thing Mussel Say, right? Say, and then sorry, I lost my /scripts. You see if yeah, under the tab there, and then activate, and then we'll hit enter. And now we know that it worked because in brackets at the beginning, right before the path, it says now brackets Mussel Say BS and then the path. So now we're in our virtual environment and we're ready, I believe, to install Kelpomatic. And so then this is where, so I have an NVIDIA GPU on my computer. If you're not sure, you can look in, actually I can show you now. If you're on Windows, we go to the device manager and we go to network, display adapters, and it'll tell you what kind of graphics. Yeah, perfect. Yeah, great, thank you. And you can look here. So I have two display adapters. One is this Intel that's sort of built into my motherboard, and then an NVIDIA. So that just depends on, because I'm not sure if you talked about this, and or perhaps you've heard it in the news, but all this imagery, well, all machine learning,
Yeah.
text too,
Yeah,
all uses these graphics cards. And so NVIDIA, big company, and yeah, so it works better if you have that.
it just makes things faster, but you can definitely still use it on a CPU.
Yeah.
But the GPU just speeds things up quite a bit, so it's just a nice quality of life improvement.
Okay, so I'm just copying that and right clicking and I'm hitting enter. And okay, what's this? Because
Oh, it's because your environment is, why it's unhappy. Oh no, this is where our demo falls apart. No,
interesting.
it's very strange. Try it without the GPU thing maybe.
Yeah, sure. We'll try it without that. Yeah, we'll just go without it for now. We'll blame the AI for that one.
Yeah, it's something to look into later.
Yeah. So I just did the one without it. It's just running now, installing these different names in the green. Those are different Python packages. So we're installing Python and then a bunch of different packages that are used for this. And you'll see, yeah, like I said, it's Kelpomatic. So in fact, when you install this, you can actually run it on Kelp imagery as well. There's just one little flag. There's one new message there too.
Yeah. Same error.
Okay, perfect.
Yeah, I mean, maybe if you ran it again, yeah, it's a new error that I haven't seen before, so that's something I'll look into.
So then now it's installed, and we can go to the running it page. And for those that are interested, also, there's a Python API, is that the right word? No.
Yeah, there's a Python API that you can do this from a Python script if you know how to use Python and want to integrate it into other workflows you have.
Yeah, like if you want to run it in batch exactly, or use other ones. So KOM is like it says here is the main function, and we can just run this to make sure it's working and find out. I'll run KOM dash help in case of that, and it will tell me something, and then we'll know that it's working. So just a little bit slow, and we can do let's see, should I do a GPU test?
I think it's not gonna work because
Not gonna work. Okay, we'll just ignore that for now. But then you can set up, this is where I find it really handy to use the notepad. So here's an example command. And so it's saying KOM find kelp. For us, we're going to use find mussels, I think.
Yep. Yeah, and maybe just worth mentioning this help thing, this dash help is really useful for getting information about, what the command expects. So if you do KOM help, it'll print up this, but if you do KOM find mussels and then help, it'll tell you what that subcommand expects. It's gonna tell us in a second here that it needs two arguments. One is a path to where your input image is, and one is going to be a path to where you want it to save what it predicts as being mussels or not in this case. There's a couple optional parameters. One is, crop size, which is just the window of data that it looks like in its image, in the image. It doesn't really process the whole image at once. It just goes in sections at a time and predicts on those, because loading the whole image is often they're too big, and it'll crash. So you can change that, or it has, defaults that are useful. Couple other useful things in here is this B flag, and so that's the model expects the images to have RGB band ordering. If it doesn't have RGB band ordering and they're using something like blue, green, red instead, you can rearrange them on the fly using this B flag, and there's an example of how to do that here. If there's any extra bands like near infrared, our Mussel model doesn't use near infrared at all, but the Kelp model does. If you specify it should. If you pass extra bands, it'll just ignore them. So you can do that, but you just have to make sure that the red, green, and blue channels are the first 3 in your image.
Yeah, thank you. So now we can build a command. I've got some, I have set the Google Drive link there. If anyone needs it, I can set it again. But I've got some folders here. I'm just gonna write out the path because this is where it's handy for me, so I should have saved it for later. So I've got a bunch of different scenes here. I can, sometimes I'll just take the pass here. And let's see, we have an output folder where I might want to put it, and we'll just copy that. And here's where we need to reformat them a little bit. So we'll get the example command. Taylor's probably cringing at the way I'm doing it, but okay, cool. Yeah, great. He'll be okay. So this is our example command here, KOM find cut. So we'll change it to find mussels. We're not going to deal with species because we don't have that option here. The crop size, that's probably fine. And here's where we're going to change this to, let's see, slash input slash so scene.tip, right? And this one can be output. And then we need to specify a name, right? So slash labels.tip, something like that.
Yeah, and your input has a dot at the beginning.
Oh,
What that dot means is that this path is relative to your current location in the terminal. And so it's optional to put it there. Also your outputs has a slash at the beginning.
oh, sorry. Thank you. Yeah, this is where I need help. Yeah.
You can also put in the full path if you wanted. You could put in c./user as well, and that would work as well. It's called the absolute path, but relative paths are often they're shorter, so we'll use that.
Yeah, and so I guess back to, I think maybe a more concise way of where I was talking about the path and environment. You can always use a full path for commands or things. Even if you're down deep in a folder, you can have a full path somewhere else. So let's copy this and paste it in and see if anything happens.
That's good on CPU.
Yeah, so it's going to be a little bit slow because it's running on CPU. So we probably won't let that run all the way because that's going to take quite a while. Usually it'll be a few minutes if you can get it to work on GPU. Yeah. But
on CPU, like maybe it will take 10 minutes. It's still much faster than doing it by hand, but yeah. Also, one question we often get is what these warnings mean, and they're just meant to be helpful prompts. In this case, there is no data value in the image. If there was, then the Kelpomatic tool knows that it can skip those areas without classifying them. And so it might run a little bit faster, but you can safely ignore those warnings most of the time.
Yeah, so we run it and then it's going to create an output, which is going to be another layer with the exact same size as your input image, where it has values of 1 for mussels and no data everywhere else. Is that right?
Yeah.
And then you can look in your GIS and interpret it and decide how well it ran. And one thing that's really nice, because it's not perfect, and especially if we're in new areas and areas it hasn't seen, you're going to end up with some editing to do. And so we've got set up in here, this is all written for kelp, but it's the same story for mussels. That of some workflows of how to deal with it. And if you're working in GIS, how to turn this into a shapefile or a feature class of some kind. So in this one, you know, it's talking about kelp, but it's just going to be 0 and 1. And some explanations here of how to convert to polygons, how to edit the outputs so you can get rid of any erroneous stuff, and reviewing and exporting.
Yeah. One thing that people sometimes bring up is they open up the output labels and in their GIS software, and they see that it is just all black. The reason for this often is because the pixel values are just 0 and 1, and so they're actually are very close to what would be black in a grayscale image. And so changing them to visualize classified, classify the pixels and visualize the different those different bins, you'll see the areas that have been classified as mussels and background. But if you leave it in, the normal visualization, you might just see a black image, but that's expected.
Yeah, my computer's working really hard. Yeah, I'm trying to think. I don't think I actually pre-created one. Let me check. See. Oh, you have to wait for it. Okay. Yeah, so besides having a look at this when it runs, that's about it. Does anyone feel free to type in any questions, bring them up here, or if you're having any issues, you can troubleshoot that. We're also happy to follow up after this via email, so send us an email. We're also happy to run imagery if you have some, because we're always curious to see imagery in new areas.
Another thing we're often interested in is if you are trying to classify mussels or kelp and are finding it works kind of poorly in your region of the world or under certain conditions, we're always kind of interested to hear about that. Especially if you're willing to share some data so that we can use it to help train our models to kind of account for those areas.
Yeah, and in fact, we can abstract the data too so that it doesn't have any geographic information. And for our training, we have orthos, over time and space, and what we ended up doing was taking sort of random chip samples all over the place to increase the variety in our data set. And so we'll take any samples, and these chips are 1024 pixels,
512.
512, so they're not very big. Yeah, but we're always happy to add in new data. Oh, it's getting close. Let's see if it's going to work. Okay, and so it's funny because we talk all about this model, and this is sort of all it is it's a couple of lines of in the terminal with some nice little colors. And add it. Add in this is what I wanted. I think this is in fact the image we use that I shared, and created some labels here. So as Taylor said, it loaded in as black, Gary, and we can change that if you're in ArcGIS. This will be useful, and if not, probably similar story in Q, but it's got values of 1. You can set it to whatever you want here. I like to use red, somehow it works fairly well. And so now we look at our results, and I was a little bit nervous to do this because I picked this up random, But it's pretty good. So interesting, here's a good example of, these aren't goosenecks probably, they're some other type of mussel. They look, the texture is a little bit different. But as we see here is a perfect example. There's probably mussels underneath this fucus, but we don't want to classify them. That would be a mistake. And here we're seeing it classify our mussel beds quite well. This here's the real intertidal science happening, and we forget sometimes to ask them to move out of the way. And it's done pretty good job, actually. Good job, Tim. Yeah, so we'll follow up with some updates. With the updates to the instructions, and if you do run this on your own data, we'd love to see the results. And again, if you want to follow up with us by email, I'll send this recording out. You can share it with whoever you'd like. And if there's any other questions, we got a few minutes. Otherwise, we're going to close. So I'll say thank you all for joining, and happy mapping. Please reach out by email, and we can follow up. And thanks to Hackeye, thanks Building Bridges, thanks to CUs, and take care.
Thanks, everybody.
Have a good day.